Hi, we are the BRG Physics Learning Device. I'm Kent Sullivan.
I'm Joseph Freppa.
And I'm Wade Titterton.
Okay, for those of you who don't know, the BRG Physics Learning Device is a product that seeks to improve the learning and understanding of physical science, physics, in the 11th and 12th grade classrooms. We'd also like to attempt to increase their interest in STEM-related fields. So just to make that stand out, we're trying to teach a bunch of different physics concepts in the 11th and 12th grade, and we really want to increase their interest in STEM. Now, in this project, we'll be going over DP1 and DP2, looking at the major takeaways from those design phases. And then in DP3, we'll be getting into the 3D CAD model and have a discussion of that. And we'll continue with design for the environment, product architecture, industrial design, assembly time worksheet, cost worksheet, and then we'll finish up with a discussion of potential future changes.
So for DP1, some of the things we went over was we gauged customer interest in what they were looking for in a product, which gave us some general ideas and things we were able to come up with and see where we were heading with the BRG. And then another thing we also did is a preliminary economic analysis to see if this product can be profitable and some of the places where we can make money and some about where we were going to price the BRG.
For our DP2 analysis, topics that we covered were intellectual property, product decomposition. This let us break apart our ideas into chunks and analyze what's moving through them. Is there matter like a ping pong ball moving through them, or are we energizing them somehow with an Arduino? We also did concept generation, and from there we used concept screening matrices. This allowed us to refine what chunks we're going to put together in our final project based on our and our customer specifications. We then did an economic analysis, and from that economic analysis we were able to find out that we could get a 16% MAR at 400 units sold that year, each year I mean. And we also, in the DP2 section, looked at prior art. So we did research on patents to make sure that we weren't infringing on other people's ideas. Now we're going to be moving into DP3 section. Here is a CAD model of our final BRG. The ping pong ball will come in, hit a switch that will send an electrical signal to the Arduino. From there, the Arduino code will tell this servo right there to trigger the mousetrap by pulling on a string attached to the hair trigger. The mousetrap lever arm will then start to swing open, to which it is attached to a pin holding back a preset plunger. The student will have to figure out where they need to set that plunger in order for a ping pong ball to be launched up and around this track that will illustrate a circular motion. After it goes around that track, it will go into the horizontal projectile motion section. The student will have to preset how far this horizontal beam there needs to be set out so that the ping pong ball can fall into its target, that cup down there. Once the ball makes it through the cup, it will then go past these two sensors. The first sensor will take the time at which the ball passes it, and the second sensor will do the same. Then the program will spit out the time difference. From there, the students can take a ruler, measure the distance between the sensors, and do an average velocity calculation. So the general gist of design for environment was to figure out what materials were more eco-friendly and that would have a life cycle that could be reused later in their lives. So we mostly used cardboard in our design because we knew that not only could we, as a company, get it for cheap and recycle it and mold it into the parts that we need in the future, but it also, for our product, after a student or a teacher was done using it, maybe after 5 or 10 years of use, they were moved on to a different product, the parts could be easily disassembled because they are held together with light adhesives like tape and recycled and maybe become a different product in the future.
Okay, moving into product architecture, you'll see we have our product architecture figure right here. Basically what this is doing is it's taking individual elements of our BRG and clumping them together into chunks. Now, the way we arrange these elements was primarily based off physical relationship to other elements as well as main overall function. So you'll see here in the obstacle 1, you have the plunger loop-de-loop track connector. Their main goal is to get an inserted ball all the way through obstacle 1. So that was a big reason why they were put together. Now the plunger and loop-de-loop have secondary functions. The BRG is supposed to teach different physics concepts, so each of those has their own, but that can just easily be thrown into obstacle 1. Now the nice thing about our chunks or clunks is that they allow for interchangeability. We can design all kinds of different obstacles and easily take maybe obstacle 2 out and put a new obstacle in. This allows for various assortments, different designs, and it can really create a family of products that we could put on the market, and not to mention a platform to build upon into the future.
So here we have our industrial design, and went through 5 categories and ranked them from low, medium to high. You can see our scores all right here. I'll briefly go through and give a couple bullets on why each category got the score it got. So for quality of user interface, received a score of medium because our product is easy to use and easy to work with, and there's no real problems, except the plunger and spring are fairly strong and can be difficult to manipulate at times. And now for emotional appeal, we received a low score, and that is because our product is not that maybe appealing to some of the materials we use, such as cardboard, some woods. And then, so ability to maintain and repair the product, received a score of medium because there's no really ability to repair but each product can be replaced due to its modular construction, and each piece individually is not that expensive, so it's fairly easy to swap one out if one breaks and keep using the BRG instead of having to replace the whole thing. And then for appropriate use of resources, got a high score because we worked hard as a team, used everything we had at our disposal, and put together a BRG we are very proud of. And then for product differentiation, we feel we have a very new and unique product to the market, and is much different than some of the current physics aids that are out there, which are just basically carts and photo gates. And we think this is a much better and engaging device for students to learn physics.
Okay, moving into failure modes and effect analysis, we had 2 major concerns that we detected, and the first one is the loop-de-loop. We were a little concerned about it being deformed, getting kind of worn, and just overall being unstable. Now, that causes a big problem for us because if the ball can't complete the loop, it can't complete obstacle 1. If it can't complete obstacle 1, it can't complete any obstacle in the BRG. And the overall mission of the BRG is to provide a learning environment for all sorts of different concepts. If you can't demonstrate the first one, it all just sort of falls apart. So it's really important that we nail it right at the beginning. And the way we wanted to fix this was just add more stability through different support mechanisms, or even just use stronger materials. Now that was our concern that had the highest RPN, but arguably our plunger, although it had a lower RPN, just mainly due to occurrence, it might be more of a concern. Our plunger consists of a mousetrap, and that could easily cause the user some harm. So we definitely would want to put some sort of safety guard or cover on that, as safety should definitely be a priority.
Now here we have our assembly time worksheet and cost sheet. In the top corner here we have our assembly time worksheet, which we use the tables provided to us to predict assembly times for each component, and add those together to get our total assembly time, which was 40.1 seconds, which is fairly quick and should leave us no problems, and we should be able to have enough workers and employees to produce enough BRGs for our liking and at the rate we can sell them. Now with this completed, it allowed us to get a much more accurate picture of our cost sheet, because now we can have predicted assembly times, which can much more accurately give us our labor times, and this gives us labor cost. So we have a total cost here of $28.08, and this is fairly cheap and right around the mark we predicted at $30, using general estimates. And if we price it at $50, we should come out with more than what we were looking for our revenue, and well then just sell 400 units to give the 16% MAR that we promised our investors at the beginning.
Okay, so some of the potential changes we'd like to make for the BRG include different material, manufactured parts, as well as a more defined board. The different materials and machine parts would allow us to not only improve the adhesives of our design, but to also improve the dimensioning, just the overall shapes, and really help our BRG function a lot more smoothly. Now, the more defined board would give us something to sort of build around. Right now, when we put the BRG all together, it takes time to put the placement, get the calibrations just right, and this would basically erase that setup time. And it would also allow us to hide more delicate parts like wiring or the Arduino. Now, as we move into our future engineering classes, some of the analyses that we think would be good to apply to this project are along the lines of a structural wear and a strain stress analysis. These would just help us to make sure that our BRG is capable of withstanding everyday use or even unintended use, just to make sure we're giving our customers what they're expecting and the BRG functions to the best of its ability. Now, what still needs to be done? A safety analysis. We talked about it earlier. There are some safety concerns with our BRG. We should definitely put some protective guards or railings of some sort over the plunger, and maybe even put some see-through, plastic covers over parts of the BRG track that may be at risk.
In summary, our BRG is completed. From our final product testing, our BRG functions fairly consistently, and we'd like to thank VTEPS Incorporated for funding our project, and we're happy to add it to the VTEPS's educational product line. Thank you.
Thank you.